let's go to the difference between theoretical computer science and software engineering. Or I don't know if you draw a distinction, but if we look into this computer world now, is there a difference between theory, things you can say formally, and the pragmatic implementation of that theory into actual systems that people use,
Yeah.
which I guess we'll call software engineering?
So, the engineer, they're obsessed with the domain of, well, what do you want to accomplish and who are you accomplishing it for? So they live in the world of people, if they're good engineers. And they say, okay, what's the experience? How are we going to use this? Why are we going to do this? What's the commercial application? What's the non-commercial application? And you collect all these business requirements. And once you've done all of that, the better job you do, the more self-evident it is of how do we apply the toys and tools of computer science and other such things to actually resolve that. And the point of theoretical computer science from the software engineering domain is it can tell you kind of where your guardrails are. It won't make perfect programs, and there's no such thing as that, but rather it can give you a good notion and sense that your program has some desirable properties. Like you can prove that it can terminate if you're dealing with total programs, or maybe you can prove you'll never have a buffer overflow, or you won't divide by zero somewhere or something like that. Some event won't occur that'll cause a catastrophic failure in your system. But there's always this combinatorial explosion between what you can test and think about and what you can actually code. So the stuff on the left-hand side lives in a different cardinality, a different universe. There's something significantly larger there. And the tools on the right-hand side, we have property-based testing and these SAT solvers. We have all this great stuff here in formal methods land and computer science theory land, but there's only a small subset of things that they actually give you good answers about. So the balance of the two things is basically saying, well, what do you care about and what are you okay throwing away? That's the art of engineering and building these types of things. So, cryptocurrencies, we deal with these complex distributed systems that have cryptography and game theory and Byzantine actors. So the balance there is saying, okay, what can't fail in that system?
Mm-hmm.
And that's the kind of stuff that you want to apply as heavy a tool set as you can, because when that stuff fails, you either have the loss of billions of dollars, privacy, or potentially even life, depending on how these systems get adopted. But then other things, what can fail? Is it okay if the block doesn't get made, every now and then? Is it okay if your latency goes up or your network suddenly becomes asynchronous and, you disconnect from it and you have to restart the computer or something like that? That's probably okay. It's an inconvenience and burden to the user. And if you actually try to chase that tail, you'll end up spending 10 years chasing phantoms and ghosts. And meanwhile, the whole world moves on. So it's really figuring out those balance of the two. And what's really beautiful is that the formal methods tools have gotten so much better over the last 20 years in particular, mostly because of incredibly high investments from Microsoft and Google and big universities, because these guys are building these gargantuan systems. If you look at the Googleplex or what Amazon has or others, and they have so much value, so many users, so many things going on, and no person can keep that in their head. And so you're talking about systems may have 10 million lines of code, 15 million lines of code, millions of nodes connecting, faulty processes happening all the time, hackers breaking in on a regular basis. So when you're trying to model all of that, trying to ask yourself, what formal guarantees and properties can I get to simplify this system as much as possible? So instead of the applications of formal methods slowing you down, in many cases, it actually massively reduces your debugging time and your ability to find where errors occur. In some cases, you can't find where errors occur inside these massive concurrent systems. And you say, well, where are cryptocurrencies going? We're talking about just the same thing, but we're talking about a much more hostile operating environment, where instead of it running in a pristine data center in California somewhere, it's running on your cell phone. It's running on your mom's phone. It's running your dad's phone. It's running on, some computer in Mongolia that may have good internet on Tuesday, but not any other day. So when you live in that kind of environment, you really do need to think carefully about a whole new class of protocols. And then you need to think carefully about a whole new class of tools and techniques to test the reliability of those systems. And you need to separate the world and say, what is high assurance and cannot fail? Because if it fails, people lose money. And what is low assurance? And it's okay if that falls apart. The other thing I'll mention is there are perverse financial incentives in our industry. Because the reality is when something blows up, the people who built those things that blow up usually get paid up front. So what they're focusing on is time to market, speed to market, and getting tokens out and getting them liquid. And then people come in, they buy it, but if there's a nascent bug in some DeFi protocol, it'll probably be discovered 6 months later or something like that. It blows up, who suffers? The users.
They already got, the people that created that already got paid.
Exactly. That's why you pay the guy who makes the brake software for your train last. And you make sure he rides the train every day.